On March 10, 2019, a brand new passenger jet plunged into the ground minutes after takeoff, killing everyone on board. It was the second time the same aircraft model had crashed in less than 5 months. By the end of that day, aviation authorities around the world began grounding an airplane that had been sold as one of the safest and most efficient in commercial history. At the center of the crisis was Boeing, a company whose name had long been synonymous with engineering rigor and safety margins measured in decades, not quarters. The aircraft was the 737 MAX. It had been designed to move quickly, certified quickly, delivered quickly. And after the second crash, it was stopped everywhere. Airlines cancelled flights, regulators reversed approvals, pilots questioned systems they had been trained to trust. Families demanded explanations that no technical briefing could satisfy. What made the situation extraordinary was not just the loss of life. It was the realization that the crashes were not caused by weather, sabotage, or a rare mechanical failure. They were linked to a design decision. A system intended to make the aircraft behave like earlier models had taken control repeatedly, without pilots fully understanding why. Within days, Boeing's assurances began to unravel. Software updates were promised, explanations shifted, internal documents surfaced. The narrative moved from isolated accidents to systemic failure. The question was no longer whether the plane could fly safely. It was how a company built on safety had allowed such a risk to exist at all. To answer that, the story does not begin with the crashes. It begins years earlier, with a race that Boeing believed it could not afford to lose. For decades, Boeing's commercial aircraft business had been defined by continuity. The 737 platform, first introduced in the 1960s, had evolved gradually through multiple generations. Airlines valued it because pilots could transition between versions with minimal retraining. Regulators valued it because changes were incremental and well understood. That continuity was a competitive asset. By the early 2010s, however, it came under pressure. Rising fuel prices pushed airlines to demand more efficient aircraft. New engine designs promised significant savings, but they were larger and heavier than those used on earlier models. At the same time, Boeing faced intensifying competition from Airbus, which had launched a fuel-efficient update to its narrow-body aircraft. Airlines responded quickly. Orders shifted. Market share was at risk. Boeing's response was shaped by urgency. Designing a completely new aircraft would take years and billions of dollars. It would also require extensive pilot retraining, a cost airlines were reluctant to absorb. Speed mattered more than reinvention. The solution was framed as evolution. Instead of a clean-sheet design, Boeing chose to update the existing 737. New engines would be mounted, aerodynamics would be adjusted, certification would build on prior approvals. The goal was explicit: match the competitor's efficiency while preserving the operational familiarity that made the 737 attractive. Deliver quickly, minimize disruption. On paper, the strategy made sense. Airlines placed orders, production schedules filled. The aircraft was marketed as a seamless upgrade rather than a new platform. But the decision imposed constraints. Larger engines altered the aircraft's balance and handling characteristics. Changes that might have been addressed structurally had to be managed within the limits of an airframe designed decades earlier. Those constraints would shape every decision that followed, and they would concentrate risk in places few outside the program could see. The core decision behind the 737 MAX centered on preserving similarity. Boeing needed the aircraft to fly like earlier versions of the 737, even though its physical configuration had changed. Larger engines were mounted higher and farther forward on the wing, altering how the plane behaved at certain angles of attack. Those changes introduced a problem. In specific conditions, the aircraft had a greater tendency to pitch upward. Left unaddressed, that behavior could require pilots to undergo additional training, undermining one of the program's central selling points. The response was software. Rather than redesign the airframe or require extensive pilot retraining, Boeing introduced a system intended to automatically adjust the aircraft's behavior. It would activate only in certain flight regimes and apply small corrections to keep handling consistent with previous models. The system was called MCS. Its purpose was narrow. It was not presented as a safety feature. It was framed internally as a handling aid, designed to preserve continuity across the 737 family. That framing shaped critical choices. MCS relied on input from a single angle of attack sensor. It was given authority to move the stabilizer without direct pilot command. Its behavior was not emphasized in pilot manuals or training materials. The assumption was that it would rarely activate, that pilots would not need to think about it, and that any failure scenario would be manageable within existing procedures. Those assumptions were accepted because they supported the larger objective: speed. By minimizing changes visible to regulators and airlines, the aircraft could be certified quickly. Pilots could transition with minimal additional training. Customers could begin operating the plane without costly delays. The trade-off was concentration. A complex aerodynamic issue was addressed through software logic layered onto an aging platform. Redundancy was limited. Transparency was reduced. What appeared to be a contained engineering choice became a structural dependency, one that would only reveal itself under conditions few had fully explored. The early warning signs did not arrive as accidents. They appeared as fragments. Test. Pilots noted how aggressively the system could respond under certain inputs. Engineers discussed edge cases where sensor data might be unreliable. Some internal communications raised questions about how pilots would recognize and counter unexpected stabilizer movement. Those concerns did not stop the program. Certification moved forward through delegated processes that relied heavily on manufacturer documentation. The system's scope was narrowly defined. Its authority was not treated as novel. Redundancy requirements reflected that classification. Pilot training remained minimal. Many crews learned about the aircraft through brief tablet-based updates rather than simulator sessions. MCS was not highlighted as a distinct system requiring specific attention. The assumption held that existing procedures were sufficient. Once the aircraft entered service, initial operations appeared routine. Then reports began to surface. Pilots described uncommanded nose-down movements shortly after takeoff. Trim systems behaved in ways that were difficult to reconcile with expectations. In at least one case, a crew managed to stabilize the aircraft by following memory items, but the event raised questions. The first crash occurred in October 2018. Investigations focused on maintenance records, sensor replacement, and pilot actions. The aircraft was not grounded. The manufacturer emphasized that procedures existed to manage stabilizer issues. Internally, analysis continued. Data pointed toward repeated activations of the same system. Sensor input, once corrupted, triggered a cascade of responses. Recovery required rapid recognition and precise execution under stress. Publicly, the framing remained narrow. The crash was treated as isolated. The aircraft continued flying. Production increased. Orders remained in place. But the conditions that allowed the first accident were not unique. They were embedded in the design, and they remained unchanged. The turning point came less than 5 months later. In March 2019, another 737 MAX crashed shortly after takeoff under circumstances that closely mirrored the first accident. Flight data showed similar patterns. Sensor readings diverged. The same control system activated repeatedly. This time, the parallels were impossible to ignore. A design issue that had been framed as manageable now appeared systemic. Regulators who had deferred to existing certifications began to reassess their positions. Within days, aviation authorities across the world grounded the aircraft. The United States followed last. When the grounding became global, the assumptions underpinning the program collapsed. Airlines demanded answers. Pilots questioned training. Lawmakers opened inquiries into the certification process itself. Attention shifted to the relationship between Boeing and Federal Aviation Administration. Investigations revealed how much authority had been delegated back to the manufacturer. Key details about MCAS, including its reliance on a single sensor and its expanded control authority, had not been fully communicated. What had been treated as a minor system was now central to the aircraft's safety profile. Internal communications surfaced, showing concern about schedules, training costs, and competitive pressure. Decisions once described as technical appeared increasingly shaped by business constraints. Boeing announced software changes. MCAS would draw from multiple sensors. Its authority would be limited. Pilots would receive additional training. But the fixes came after the damage. Production was halted. Deliveries stopped. Completed aircraft sat grounded. The crisis was no longer about a single system. It was about trust. And trust, once lost in aviation, does not return quickly. The consequences unfolded over years, not weeks. Boeing halted production of the 737 MAX in early 2020. Airlines cancelled or deferred orders. Compensation agreements were negotiated to cover grounded fleets, lost revenue, and operational disruption. The financial impact escalated. Boeing recorded charges that eventually exceeded $20 billion related to the program. Cash flow turned sharply negative. Debt increased. Share buybacks were suspended. Management was reshuffled as pressure mounted from regulators and investors. The human cost remained central. Families of the victims pursued legal action. Investigations documented how a combination of design decisions, certification gaps, and communication failures aligned. Settlements were reached. Criminal charges were filed against the company, later resolved through agreements that included fines and compliance obligations. Regulatory processes changed. Certification authority was re-evaluated. Oversight increased. New rules limited the extent to which manufacturers could self-certify critical systems. Training requirements expanded, reversing years of emphasis on minimal transition costs. Airlines faced their own adjustments. Pilot training schedules were rewritten. Simulator time increased. Fleet planning was disrupted. Confidence in delivery timelines weakened across the industry. When the aircraft was eventually cleared to return to service, it did so under stricter conditions. Software was modified. Redundancy was added. Training was mandatory. But the pause had already reshaped the program. What had been designed for speed now moved cautiously, under continuous scrutiny. The cost of the original urgency had become permanent. When the 737 MAX returned to service, it did so in a different environment. Regulators imposed conditions that had not existed before. Pilot training became mandatory and standardized. Certification reviews extended beyond technical compliance to questions of process and culture. The aircraft flew again. But the program never regained its original framing. What had once been marketed as a routine update was now treated as a distinct aircraft with a defined history. Airlines adjusted expectations. Delivery schedules were renegotiated. Every system change was examined with a level of attention that had not existed at launch. Inside Boeing, priorities shifted. Engineering authority was rebalanced. Internal reporting lines were altered. Safety oversight was elevated as a formal function rather than an implicit assumption. The company emphasized that the failures had been addressed. Yet the context had changed. The crashes had revealed how pressure, continuity, and delegation could interact in ways that were not visible on any single document or decision. No single moment defined the outcome. It emerged from alignment. When speed became the dominant constraint, trade-offs accumulated quietly. The aircraft did not fail because safety was ignored outright. It failed because safety was treated as stable while everything around it was moving faster. By the time the consequences were visible, the system had already committed. The grounding did not mark the beginning of the crisis. It marked the point where it could no longer be contained. And long after the aircraft returned to the sky, the question it raised remained unresolved. How much complexity can be managed when time itself becomes the primary design parameter?